Okay, so we saw the list implementation using an array as well as a single linked list, and I also introduced what is called a double linked list, right? So a single linked list has a sequence of nodes like this, inserted or connected using the next node pointer address. Now a double linked list has okay, let me use this slide. Okay, so a single linked list has each node the data that we want to store and the next node pointer address value. So pointers always we store addresses, so we assume addresses are going to be 4 bytes in size in this course. So if the data is an integer, that's going to be also 4 bytes. If the data is a double, it's going to be 8 bytes. If the data is, say, an object like the packet object, it's going to be whatever the size required to store the member variables of that object. So that's how we decide the size of a node. So in this example, the size of the node here is 4 bytes for the integer plus 4 bytes for the pointer address. So it's going to be 8 bytes per node for a single linked list to store an integer as part of the data. Now in the case of a double linked list, it's going to take up 12 bytes because we have 4 bytes for the previous node pointer that stores the address of the previous node, then 4 bytes for the next node pointer storing the address of the next data node, and then the data itself in this case is like 4 bytes, so that will be 12 bytes for a double linked list. So in terms of overhead, if you want to just store a list of integers, if you use an array, this memory that you will allocate is just to store the integer. So with an array implementation, each each node, if you want to think about that, each unit is basically going to be just the data itself. So it's 4 bytes there. Whereas with the single linked list and double linked list, you're allocating more space for every data unit. So that's what I'm representing here. So the single linked list, that for integers, it's 4 bytes for the data, then 4 bytes for the next node pointer, and there's no previous node pointer in a single linked list. So totally each node is going to be 8 bytes. So an array is going to take just 4 bytes. So the percentage overhead that you get with a single linked list is 100%. So how you get the 100% is basically 8 minus 4 divided by 4. 4 is array is our reference. So 8 bytes for a single linked list minus 4 bytes for an array divided by 4. So it's 100% more than what we need for an array. Now if you are storing an object, let us say it's 32 bytes in size, and then the next node pointer is going to be still 4 bytes because you are storing only the address of the next data node. So that's going to take only 4 bytes. So the total node size is 36 bytes for a single linked list to store an object of size 32 bytes. So you can see here, since the next node pointer value, the size is not increasing, the amount of additional memory you're going to allocate for a node in a single linked list is not that much high. It's going to be 36 minus 32 because that's what you have to allocate to store as an array. So 36 minus 32 divided by 32. So that's going to be 4 divided by 32, which is 12.5%. So the percentage overhead is not that much high compared to the overhead you encounter in storing an integer. So this itself gives us an idea from a memory point of view, when can we go for a single linked list based implementation and when can we go for an array based implementation. So if you want to save memory, that's your prime objective, then you can just go for an array based implementation. Whereas if you are willing to spend some additional memory and accomplish things that we can accomplish with this linked list, the main thing that we can accomplish with this linked list is we need not worry about the available of consecutive blocks of memory. Okay, with an array based implementation, if you want to store a lot of elements in your list, then you have to worry about am I going to have sufficient block of consecutive blocks of memory available in my for storing my array. With a single linked list, you will not encounter that problem of memory not being available to store your nodes, because you're going to create only one node at a time as you need. So you don't need to really allocate a large block of memory for this list. Now, a double linked list, you have the additional overhead coming through the previous node pointers. So to store an integer, you really need 12 bytes rather than 4 bytes with an array. So the overhead is going to be 12 minus 4 divided by 4. So that's going to be 200% overhead. Whereas if you store an object of size 32 bytes in a double linked list in each node, then it's going to be 32 bytes for that object, that's the data, then 4 bytes for the next node pointer and 4 bytes for the previous node pointer. So that's going to be 40 bytes. So that's like 25% overhead. Okay. Now let us see this slide and then we'll look at this code here. So we saw from a memory point of view what's the kind of trade-off between the linked list and an array. So let us now look at the time complexity point of view for the different operations that we can do on this list. So the key thing is, or the two main types of operations that we can use to compare is just reading the list or doing any insertion or deletion to the list. So reading the list is like, so you build the list initially and fill up with all the numbers, all the elements that you want, and then if read or modify is the operation that you typically do after you build the list, what kind of data structure do you want to use. Or even though you build the list initially, you will be doing more frequent insertions and deletions dynamically as you get inputs from the user and all these things. Then what kind of data structure you would need. Okay, so that's how you will look at this comparison. So if so you see, what I have listed here is the time complexity for the different operations with the data structures, and we have seen this as we went through the code. With an array, you can read any element of the array, any element at any index in the array in constant time, so data of one time. So remember, with an array, you can always use a base address and go to that element at that particular base address. You don't need to traverse all the elements in the array and then access a particular element. So if you want to access, say, array of 10 in a list of, say, in an array of 100 elements, once you have the base address, say 200 plus, so if you're storing integers, it's going to be 4 bytes per data unit. So 4 times 10, 240 is going to give the address of that particular index element. So you can access that element right away instead of going through elements at index 0, 1, 2, 3 and then reaching the element at index 10. Now, whereas you cannot do that with a single linked list or double linked list, because with a single linked list, even in the double linked list, you have to start always from the head node in a single linked list. The double linked list, you could start from the head node or the tail node, but so let us focus on single linked list. At the same time, complexity will almost hold for a double linked list. So in a single linked list, how do we do the read operation? We have to start from the head node and traverse through every node, one node at a time, until we reach the node at the index that we want to read. So at the worst case, you will be traversing the entire list. Okay, so you cannot do anything in constant time. Like the time you spend to read a particular index is depending on where that node is in the list. So accordingly, we have to traverse the entire list at the worst case, starting from the head node. So that's why I put here big O of n as a time complexity to read or even modify. So if you want to modify the data, so again remember, modify is different from insertion. So modify means you're not adding any new data, new node. You're just changing the data at a particular node at an index. So modify, the code to do the modify is going to be same as the code to do the read. So we saw that last time. So to do that also with the list, you have to traverse the list and reach that node that you want to modify the data. So it's also big O of n time. Similarly, so that you'll encounter big O of n time to read or modify a double linked list. So as you can see, then for reading and modifying a list, most of the time you would prefer an array based implementation. Now for insertion, for all the three data structures, you need big O of n time. Single linked list, it's very obvious, you have to start from the beginning and go through the list until we reach that node. Now we saw for an array the time complexity for insertion last week in the class. So how do you do insertion with an array? You have to So you have to copy every unit, every integer to its right, like this, and then insert, overwrite the data at that index that you want to insert. So you will do the shifting or copying the values to the right to create the space for insertion. Now if you really want to insert at index 0, that's the most time consuming position for insertion. If you want to insert at the end of the array, all we have to do is just write the data next to the end of array variable. So if your array has currently 4, the end of array is 4, that's where the last element is, you can insert at index 5 by just writing that value there. You don't need to do the shifting. But if you want to insert at index 0, you have to shift every element or copy every element to its right all the way up to index 0 and then write the data there at index 0. That's how we can create space for one new element and insert that element. So insertion is time consuming with an array, especially at index 0 or the beginning of the list. Similarly, deletion is also a time consuming operation with an array based implementation. So if you remember the logic of deletion, if you want to delete the element at index 0, then you have to copy, starting from the next index, the elements at index plus 1 back to element at index. So if you want to delete at index 0, you have to shift or copy the 23 to its left, then 13 to its left, and then 17 to its left, and then 37 to its left. So again, we have to do this copy operation n times at the worst case if you want to delete at index 0. On the other hand, think about a single linked list, the implementations that we went through. So if you want to insert at index 0, I think I explained the code for this last time, someone asked it. So look at this process. Let us see insert at index. So if you want to insert at index 0, set up the two pointers, current node pointer and previous node pointer. So current node pointer will be actually null because if you don't have any data, or let us assume that there is some data, so that doesn't matter. Let us assume that a list has 10, 5, 7, 9 and still you want to insert something at index 0, and then basically whatever the data you insert, say 30 will be the first node data in the list, so it will become 30, 10, 5, 7, 9. So how that's going to happen? So current node pointer will initially be this 200, and previous node pointer will be storing the address of the head node, that's equal to 100. So index is 0. Current node pointer is not null, get inside, 0 equals 0. So you want to insert at index 0. So you break from the loop right away, don't go through the loop at all. And then insert our new node. So set up the node with data 30 and then set the new node pointer's next node address to be the current node address. So new node pointer will be set up, its next node will be next node address will be set to 200. That's the node where current node pointer is pointing, and the previous node's next node address is set to the new node pointer. So the previous node next node address is 200, it's overwritten with the address of the new node. So that means from the head node you will traverse the new node and then go to the current node and move on. So that's insertion at the beginning of the list. So this can be done without going through a loop of traversing the entire list. So we can say this can be done in constant time. So your list could have 1 million elements, and if you still want to insert at the beginning of the list at index 0, you just spend the same amount of time as if the list has just 10 elements or any number of elements. So it doesn't matter how many elements you have in a single linked list. If you want to insert at index 0, you spend constant time, same amount of time. So that's what I indicate that with theta of 1. Similarly, deletion, you can isolate the first node with constant time without going through the while loop. Okay. So insertion or deletion with a single linked list is going to take only constant time if you want to insert and delete at the beginning of the list. But when you write the time complex, you have to consider all the possibilities. So you could insert at the end of the list. In that case, you would have to traverse the entire list and then insert the new element at the end of the list. So in general, you can say big O of n time, but you have to know this trade-off. With an array, it's the opposite. Inserting at the end is more easy. You don't take much time. Whereas inserting at the beginning of an array is going to take a lot of time. So you can say big O of n. Whereas with a single linked list, inserting at the beginning of the list is not going to take much time. Whereas inserting at the end of the list is going to take a lot of time. So that's the trade-off you have to understand between an array and linked list based implementation. So these things you should know when you go for interviews. They may ask you how you compare the linked list with an array implementation. Okay. Same thing with deletion. Right. Now, checking if the list is empty with an array based implementation, we can use the end of array variable to check if it is -1. That means there's no, because end of array is going to store the index of the last element that is in the array. And if it's -1, that means the array has no elements in it. So you can check if the array is empty. Similarly, in a linked list case, you can check if the list is empty by checking the value of the head node's next node pointer value. So we wrote this function is empty. So if the head node's next node pointer is null, that is similar to having an empty list. So this is a head node, its next node pointer is 0. That means it doesn't store the address of the next data node. So if it is null, it means the list is empty. Okay. So we can do that also in constant time without going through a loop. So this is empty can be done in theta of 1 time for all the three data structures. Now counting the number of elements in the list. So if you want to count the number of elements in the list, with an array based implementation, we have the max size or end of array that can give you an accurate count of the number of elements in the array. Whereas in a single linked list, we don't keep track of the number of elements using a separate member variable. So you have to traverse through the entire list and then find out how many nodes are there, because since you can add and insert or delete any nodes dynamically at runtime, we cannot have a feature like max size like we have in an array to find out the size of the list or the size of the array. Whereas in a single linked list, you don't have that feature, so you have to traverse the entire list to count the number of nodes in the list. And you can accomplish that similar to the iterative print function. Just have a member variable, say int count equals 0, and every time you go through a node, you increment that count until you reach the end of the list, and then return that count as the return value of this function. So that way you can count the number of elements in the list by traversing the list. So that's going to be big O of n time. Now a double linked list, you could traverse from the head node or a tail node, but still you have to traverse the entire list. So that will also take big O of n time. Okay. So this is a very important comparison that you have to understand. So if your objective is to save time, and most of the time you do only a read operation, then you go for an array based implementation. Whereas if your objective is to save memory and also don't need to worry about the availability of memory, especially if you're working with a very large list, then you go for a linked list based implementation. And also if your objective is to be able to insert the beginning of the list more efficiently, then go for a single linked list. If you want to always keep adding elements to the end of the list, so if you want to insert always at the end of the list, then you go for an array, because that's going to be less time consuming. But you have to remember that the memory may not be available all the time if you work with a very large array. Okay. Any question on this comparison? Okay, let me save